Okay, so apologies for the slightly odd setup today. So I'm going to give a brief introduction to Lisp. The idea is Lisp for beginners and generally Python programmers. Right, so I'm not going to assume too much, but I'm not going to try and go into too much detail either. I'm just going to try and give some nice ideas, so maybe we can look, have an interest in it or in Lisp or not. I think generally speaking, Lisp is a fairly interesting language for historical reasons, if nothing else. So I'll go into that a little bit as well. So let's start with the history. This is the fellow who, John McCarthy, is the father, let's call him creator of Lisp. He published, I think that's the next slide, yeah. So Lisp was published initially as a paper. It was, the story goes that it wasn't ever his intention really to turn it into a programming language. It was a mathematical curiosity. He discovered that with 5 or 6 operations, you could construct a Turing-complete language. So it's partial. I think this is part of the reason why it's very, very nice, because it's very, very minimal. It's old, 1958. It's 1 year after the first implementation of Fortran, so they were essentially around the same time. And it does show some of its age in some ways, but in other ways, I think one of the things that's really interesting about Lisp is that it is really forward-thinking. There are ideas that are becoming mainstream now that were already there in the very early days of Lisp. So I think that's very interesting. To give us some context, this is a computer from 1958. So we're talking about something that was really, really written quite a long time ago, and broadly speaking, hasn't changed too much since. So it's very close to the original notation that was written in the original paper, which is really nice. So here are some things that were originally introduced in Lisp. Conditionals. Lisp gave us conditionals. So if statements didn't exist before, in the form that we see them today, didn't exist before Lisp. Tree data structures, first implementable in Lisp. Garbage collection, it was the first language with garbage collection or automatic storage management. It was the first dynamically typed language. It was the first language with functions as first class objects. It was the first language with higher order functions. And the first with symbols as types. So that I will see a little bit more about what a symbol is and what that means. It introduced the concept of variables as reference to some object rather than variables being essentially substituted by the value at compile time. So that's really nice. That's something that's prevailed. It's literal data structures. First introduced literal data structures. I remember writing these words and I remember thinking I'll abbreviate them in a way that I understand so I can explain them, but I can't remember what I meant by that. Literal data structures. Ah, right, yes. The literal data structures, as in, so arrays, data structures that we can write as part of syntax. It was the first language to have complex composite data structures written as syntax. It's the first language with multi-character variable names, so that's something quite fun and interesting. The first language to support recursion. It has the first self-hosting compiler, so the first compiler that could compile itself. So you can write the code for the compiler, and the compiler can compile the code for the compiler, which I think is really, really neat. It's the first language to have, and once we've made that statement, it's fairly obvious that it's going to be the first. It's going to have execution at compile time, but it's the first language to have an execution environment at compile time. So something like we've mentioned template-meta programming here before, so that's sort of people who are familiar with template-meta programming are probably familiar with those sort of ideas. And it's the first read, eval, print loop, so it's the first sort of interpreter as we know it today, right? And this, I think this is really, really cool because there's lots and lots of stuff that we get from this language, which is usually quite considered to be quite an old, ancient, possibly boring language or complex language. In terms of popularity, this is one of the only things I could find on the popularity of Lisp. So the first thing you'll notice is I haven't circled there's no entry called Lisp. There are just dialects of Lisp. And Lisp is one of these languages, from the way that it's implemented, because it's quite easily extendable. And one of the things that people tend to do fairly early on in their Lisp career is write an interpreter. So there are thousands and thousands of, let's call them dialects of Lisp. There are some that are quite common. Generally, the pattern in Lisp tends to be that someone extends Lisp to be the way that they always dreamed the language would be. And then they go, okay, and I'm going to implement that in C. So that's a fairly common thing to happen. These are scheme common Lisp, eLisp probably the more common. Racket is a bit of is derivative, but a little bit different. Closure again, it's a bit different from the kind of common Lisp.
So what are these two axes?
Sorry, yes, very good point. So this is I call this popularity. This is the number of questions on Stack Overflow,
okay.
And this is the number of pull requests. So generally, up here is top right is popular, bottom left is not popular. It's not very good. It's not a perfect metric, but it gives the idea. And part of the idea I wanted to get across with this is that it's not one of the most popular languages. It's not up there with Python, PHP, Ruby, Objective-C. I'm surprised Objective-C is that high, but there we go. The shell. It's sort of in this secondary group, but neither is it down on the bottom left. So it's alive. It's alive, but not massive. For some context, Fortran, which is the other contemporary, so these are generally considered to be the two oldest languages in common use, Fortran and Lisp. And they're relatively, they look as if on this plot at least they're similar popularity, although we are comparing one Fortran against 5 Lisps. Oh, and Julia. Julia's interesting. Julia's been mentioned a few times. Julia, lots of people, one of my favourite things about Julia, and why I quite like it a little bit, is that it's derived quite heavily from Lisp. Part of Julia is written, the syntax part of Julia, I think it is written in Lisp. And there's some nice concepts that we'll see today that are borrowed from Julia. So it's another example of languages that tend to be continuously taking features out of this very, very old language, which I think is really nice. So what is Lisp and how does it compare to Python? So in order to do that, I found online a very, very nice passage written by Peter Norvig, in which he'd taken the python.org blurb that described why Python was good, and he'd translated it for Lisp, which I thought was really, really quite cool. So, as you see, blue is Python, what was there before, green is what's Lisp. So Python, or Lisp, is an interpreted and compiled. In the case of Lisp, Lisp is also compilable and compiled. Object-oriented, high-level programming language with dynamic semantics. It's high-level built-in data structures combined with dynamic typing and dynamic binding make it very attractive for wrapped application development, as well for users for script and blah, blah, blah. They're both simple to use. They're both easy to learn syntax, in Lisp in particular, and therefore reduces the cost of program maintenance. So that's quite nice. I'd like to point out the interpreted and compiled. This is one of the really cool things about Lisp, is that you can, as far as from the programmer's point of view, a call to a compiled function and a call to an interpreted function can happen in the same runtime, which is one of the really nice things. And functions can go from interpreted, they can go from not compiled to compiled on the fly, and you can control that. That's one of the really cool things about Lisp. Lisp supports packages. They've got an extensive standard library. There's just going on a bit about this. Often programmers fall in love with these two because they increase in productivity. Since there is no separate compilation step, because remember we do have a compilation step, it's not necessary. Debugging is easy. The edit test debug cycle is really fast. We get stack traces. And this, I think, is the final one. We get source level debuggers, local and global variables. So, I mean, the point here is that Python is an interpreted language, but we have Lisp, as far as this description goes, it has all of the same benefits, but we can also compile things. Some benchmarks I've seen seem to imply that Lisp is around 2 times slower than C, whereas Python is obviously into the hundreds. So it's nice that we can do this. There are some costs, but we'll talk about that in a little bit. So the Lisp language, what's it like? So the first thing we're going to talk about are atoms, and atoms are kind of, it's something that you probably wouldn't even have a word for in another language. They are really simple. They're basically the smallest building blocks of syntax. We call atoms. Atom is something that evaluates to itself. So the number 1 would be an atom. The character A. Let's go through some. Number 1 is an atom. Float. A float is an atom. A string. Symbols. So the previous 3 things evaluate to themselves. Symbols. We normally think of them as variables. Now, the concepts have to be a bit different here, but fundamentally, the idea is it's a variable. But the symbol is the thing that points to the value, and we think of them a little bit more disconnected than we normally do in other types of programming, and we'll see why later on. But yeah, a symbol evaluates to its value. Yes. So hopefully, so far, no surprises. I've got this notation here with the right arrow that is a prompt, right? So I'm doing this in a REPL. So symbols. So the symbols. Talking about symbols. Symbols are represented by a string of characters, and there are very few reserved characters. Basically, you can use almost any character in a symbol, and there are no reserved words. Right. So that's if you're used to any other language, this will be a bit different straight away. You're used to being quite strict on what can be contained in a variable name. So these 2 things are valid variable names, no problems at all. The one on the top is probably a bit weird. The one on the bottom is the thing that's used most by convention. We tend to use this sort of minus sign to separate words, which is very nice. And hopefully, as we see a bit more of the syntax of Lisp, we'll realise that it's written in such a way that this couldn't be confused with addition. So, easy. So far, we can evaluate stuff. You have something, you evaluate it, it returns, it evaluates to something. And it's useful. It'll be useful right from the start if we start thinking of the idea of a string, the way that it's represented, evaluating to an object that is the string, and separate those 2 concepts off straight away. It'll make your life in Lisp much easier. So, syntax. Lisp has no statements. There's nothing you can type that gets evaluated that doesn't return a value. Yeah, all expressions, all parts of the syntax are expressions, and therefore have a return value. Good? Happy? Easy? These expressions are written generally either as atoms or as lists. Lists are also known as forms, and these lists are called S expressions. Right? And as I said, expressions can contain atoms, symbols, or other S expressions. So a simple example, cos of 0.5. Right? We write these lists. We write a list with parentheses. Then we have a series of atoms. Right? Here we have a symbol, and here we have a representation of a float. So, evaluation rules. I evaluate the operator. The first thing I evaluated to get the procedure. So I evaluate the symbol cos to get the logic associated with cos. Right? Then I evaluate all of the operands to get the arguments. I'm going to pass. That we normally say pass. In Lisp we say apply. We think of a function application. So we then apply the procedure to the arguments. Right? And if the operands are not atoms, if they're other S expressions, they then S expressions evaluate by following the same rule. So our entire program essentially becomes this loop of evaluation and application, evaluation of application, evaluation of application. Right? Does that make sense? Quite straightforward, right? One of the nice things is that each argument evaluation is independent. and each S expression returns a value. And the key thing is here is this is all really, really simple. And fundamentally, these are the building blocks of the language, right? That's sort of almost it. It isn't almost it, but it's very nearly almost it. And if you compare that to languages like Python or C, where you have a huge amount of syntax, you have a huge amount of reservation, you have a huge amount of things that you can and can't do, here we just have a very, very simple set of rules, and from that we construct all of our computation, which is really, really nice. So, there we go. There are no operators in the conventional sense that we think about them. There's no plus or minus, they have no special meaning. Plus is a function that happens to have the symbol plus. And same for all of the mathematical, all of the equality signs. Right, so we see here all of the same, we have the same consistent way of thinking about everything, which is as a list of objects in which the first item of the list evaluates to the procedure and the rest evaluates to the argument. So there we go, plus 1, 2, plus 1, divide 1 by 2, multiplication, etc. So notice the interesting thing about this is that it results in what we call, it results in a prefix notation. So we have the operator that comes before the things that are going to be added, rather than the infix notation that we're used to. So here's an example of an expression. And I think on the next slide, yes, so it's translated. So here we've got this is sort of infix notation version, and here we have actually incorrectly the compound, the Lisp version. I've just noticed there's an extra 5 at the end. So I could have, this is 5, this expression times 5. But yeah, so to make this correct, there should have been another times 5 on the bottom. So everyone, does that make sense to everyone? So if we want to read it, we sort of work from the inside out. We've got 1 plus 10, that's getting evaluated. Then cos of 1 plus 10, cos is being... Pardon?
Then it's divided by 5, right?
Ah yes, no,
Okay.
there's actual parentheses, yes. So, sorry, I missed that out. So we've got 1 plus 10, we've got 11, cos is applied to 11, then divide is applied to 11 and 5, cos 11 and 5, and then sine is applied to the result, and then multiplication is applied to 5 and the result of that, yeah? So this is how we think about the programs. It's all really nice, it's all really clean. So I'll move on. I'll talk more about the benefits of this kind of syntax in a little while, but let's just introduce some more stuff. Assignment, right. So assignment, the correct way, the full way of doing assignment is the top one. So we got set, quote A1, right? Now remember, we need this quote because if I say set A1, it's going to evaluate A. It's going to the expectation is it evaluates A, it evaluates 1, and then it tries to set the value of A to 1. Yeah. So this is why again we're having this distinction between symbols and values because everything gets evaluated automatically. So we need to be able to say, actually, I want to pass around the symbol A now rather than the value of A. Does that make sense? And this is where we get this quote from. So we quote symbols to pass them around. There's a shorthand for this, which is the quote symbol, quote A, and there's another shorthand, set Q A1. Yeah, and you'll notice that this obeys the rules that we've described, but there are also things that don't obey the rules that we've described, right? And one of the nice things about Lisp that we'll talk about again in a minute is it has this extension mechanism whereby you can extend the language to support things that are outside of this domain, this simple domain that we've initially described. And these are two of these. These are two versions that could potentially be using that extension mechanism, but actually, in most cases, are built in. Right. So this is how we do assignment.
What are those?
Yes, sorry. So these guys are just, I copy and pasted this out of my interpreter, and that's some different representations it gives of the same value that you could use instead of 1.
Okay.
Yeah. But yeah, these things in comma in brackets with hashes is probably better just ignore them for simplicity.
Okay, so this operation, the set operation, okay, which is an assignment, actually it returns, like in C, it returns.
Yeah, exactly, yes. So here I've got set A1, returns 1, but also sets the symbol A to refer, to point to the value 1. Yeah. Makes sense. We can nest them. So we've got this program thing that allows us to, which is essentially, it's another, well, you can imagine it not doing very much, to be honest. All it does is return the last argument, right? But actually, it all gets evaluated. The one thing that this does ensure is that things get evaluated in order. But why wouldn't they? So here I've got sort of A equals 5, then I print A, then I set A to another value, then I print A, and I have it's just some value as the last expression that gets evaluated, the value to itself. So the result of all of this expression is 55, and along the way I've printed out 2 things. There's nothing too clever there. I could achieve the same thing with the list. So list is a function that constructs a list by evaluating all of the atoms, all of the parts of the form, all of the arguments. Well, it doesn't evaluate all the arguments, it just gets past the arguments and then construct it into a list. So the only difference here really is that the return values are a bit different, right? So just 2 simple examples of how we can build slightly more complicated programs. So one thing we haven't talked about yet is functions. So that was assignment and building some more complex composite programs, composite S expressions. Functions are, for people who are familiar with Python, for example, this isn't going to be too much of a surprise. We've got this defun special form. Oh, it's a macro, I think, actually. But yeah, this is built using the same extension mechanism that we described earlier. And I give it some argument. The first argument is the symbol that the function is going to refer to. Then there's a list, which is a list of the argument, of the names that I'm going to give. So the list of the symbols that I'm going to associate with the arguments. And then the final one is a list of the things that I'm going to do. So this is the list of the stuff that I'm going to do. So this is just going to multiply 7 by number, yeah? And because it's an expression, because everything's an expression, it returns the symbol multiplied by 7. And I can apply it like this, as I read in before, right? So this is just fun. This is just basically.
Suppose we have an integer and we have a floating point number.
Types.
Yeah, type.
No, there are types. There are some, but Lisps that do type. That you can have working with types, so you can have more statically typed languages, but generally it's dynamic. So generally, you don't specify type.
No, still, like say I just say in brackets multiply 2 and 0.4.
Ah, yes. So there's some casting, I think, implicitly.
I see.
Yeah.
And what would be the output?
But it has to be defined in the operator, right?
Yes. I mean, I've never actually defined an arithmetic operator, but yes. Yeah. We'll have a chat about that later, and we can look at some examples of what happens. So the key thing here is that multiplied by 7 is just a symbol that refers to something. I don't think I've done. At some point, I might have it in one of the slides, but fundamentally what we're doing, fundamentally this is essentially just assignment. It's an assignment under a different name. We'll talk more about that later. We can redefine operators if we want to. So here I've defined division to be multiplication. So the point here is that we can really easily get into trouble. We can redefine if you try this in anything, it will break, because your if statements will not work anywhere. So that's interesting, depending on the scope of the rules, of course. And then we got this. That's probably a bit earlier, but we've got this macro expand that allows us to see actually this def_fun. I've put this a bit early in the presentation, but essentially we'll talk about what macros are later. But they allow us to extend the syntax. And we can see here that this syntax has been extended by defining def_fun to be equivalent to an assignment of a lambda. So don't worry too much about that later. We'll have more of that later. So it's quite nice, right? It's a really simple model. All we have is function application, at least so far. And we can extend the language quite easily just by we define functions, and the functions. And since everything is a function, everything's quite easy to override. So a couple of asides, a couple of things to mention while we're at it. There are two types of Lisp generally. There's what we call Lisp 1s and Lisp 2s. And that means the difference is that in Lisp 1 is kind of the namespace that is more similar to the languages that we're probably more used to. So there is one namespace. If I set a equals 1, any reference to the symbol a is going to refer to 1. Lisp 2s have two namespaces. So depending on context, for a symbol, you're either going to be referring to the function namespace if you're trying to use it as a function, or to the variable namespace if you're trying to use it as a variable. So I think I've got an example. Right, so here's an example. I can set cos to 1, and then I can do cos. And it knows and if it's the first, the rules sound quite difficult, but at least to begin with, the easy way to think about it is if it's the first entry in the list, if it's the first part of the form, if it's the operator, we evaluate it to its function namespace. If it's the argument, we evaluate it to its variable namespace. So that's a slightly quirky example, but hopefully that makes a bit of sense. The other thing is the name binding. Early Lisps tended to have dynamic scope. So they tended to have scope that's defined at runtime. So for anyone who isn't familiar with the differences between lexical or static and dynamic scope, lexical or static scope is the type of scope that we're maybe more used to, where I have my scope is defined by where I write the expression in the source code. So if I write a function inside of a closure, for example, then that function belongs to its parent. If I write an expression inside of a function, etc., etc. So if I'm looking for, if I'm trying to resolve a variable, I'll look at I'll look first within my own scope, then I'll look at some parent scope that is defined statically at compile time as part of my writing the code. So for example, I'll look in a module or a package, and then I might work my way outwards, right? But for every scope, it's known explicitly the tree that's looked up. Dynamic scope is a bit different. Dynamic scope means that I do the same lookup, but I do it based on the call stack. So I'm going to walk my way up the call stack. I'm going to look at who called me, and look for the first instance of that variable. So dynamic scope was quite popular in the early days as it were. It's a lot less popular now for obvious reasons. It does result in some really nasty bugs, and it's quite difficult to debug. Some of the older Lisps are dynamic by default, so the original implementation of Lisp, eLisp. The newer Lisps, Common Lisp, Scheme, Racket, are static. Most of them do allow you to either be dynamic or static, which is quite nice because in some cases dynamic scope, although dangerous, is really quite powerful. Yes, so I think that little sentence probably sums up quite a lot of Lisp in that it's really quite powerful, but it doesn't stop you really from shooting yourself in the foot. It's quite a dangerous language, as it were. At least that's my opinion. So, name binding. The next thing is programs. One of the key central ideas that we've already seen, but we've not really talked about explicitly, is that programs here are just data. We've written a program as an array. Yes, I don't have any examples. So for example, if let's jump back and see if we can pick up some nice examples from the previous slide. So here, for example, the list. List is having let's see if I've got anything nested. I haven't got anything nested yet. Right. So let's say this list is essentially it's an array. It's a data structure that we evaluate, right? And I could easily write that Lisp as the first atom, as the first argument of another S expression, right? And when I'm going to do that, I'd have two options, right? One option would be I can put that in as it is, and then it would get evaluated, and the parent function would only see the value it evaluates to, right? So the value of this list, the previous example is probably simpler. Where is it? Ah, there's a difference. I see, I've got lost now. Right, I can't work my way around this. But so the previous example is so let's say we had so this S expression, whatever it is going to return a value, right? And then if it's evaluated, the value gets passed into the function in the parent S expression. Now, another option I could have is that I could quote that that list S expression by, remember that quote syntax that we had, so it's dash A we had, so I could say dash and then the list, and now that list would get passed around as data, right? And this is quite a powerful idea, because it means that I can use any part of my language. If I have something that iterates over lists, I can iterate over the list and change it. Yeah. If I have a symbol in there that I want to swap, if at runtime I decide, well, I've written this, but I have a symbol A that I want to swap for symbol B, I can just do that by iterating over the list and changing it, right? Introspection and looking at the code, the sort of things that we do normally in Python by looking at the AST and then trying to decipher that, it's trivially easy in Lisp, because essentially what we're doing is writing the syntax tree from the get-go. And then we can either choose to evaluate it, or we can choose to treat it as data and to manipulate it, iterate over it, change it, right? And this becomes quite a powerful idea when we use it correctly. Does that make sense? It's easy, right? Now let's see if I can find where I was in these slides. Programs of data. So, special forms. So we covered some of the syntax, we've seen a little bit of how it's built with these things. We've seen that actually this could be potentially quite powerful, but the power of it isn't, but so far everything's been interpreted runtime. We've not really gone fully into the power of being able of what we can really do by manipulating these lists. And unfortunately, because I was a bit time constrained when I put these slides together, I don't have any really good chunky examples, but there'll be simple examples and hopefully it'll be fairly obvious to deduce what's possible. So, the question now is, what if we want to redefine if correctly, and we want it to work as an if? We've got a little problem with Lisp in that we've got this function application model, this application of functions or procedures means that we have to evaluate all of the arguments first. right? So here, this is how you write an if statement in Lisp, but this doesn't follow the rules, because if I were to evaluate this, I'd first evaluate the conditional, then I'd evaluate the thing to do if true, then I'd evaluate the thing to do if false, and then I'd pass it all to if, and obviously that wouldn't work because I just evaluated everything, right? And this is an issue because we have eager evaluation. There are mechanisms built on Lisp and some dialects that people have attempted to support lazy evaluation, but generally speaking, Lisp is eager evaluation. This is known as a special form, and it doesn't follow the same evaluation rules. Okay, so this is a list of all the special forms that are available. Right? These are the ones that are built into the language. But we also have a mechanism to write our own, as I've pointed out, as I've suggested a few times. And let's have a quick look at that. That's what's called macros. Macros have something in common with C-type macros or template metaprogramming, in that they're operations that happen, in that it allows us to control at compile time some of the behaviour of the program. But as we'll see, and hopefully as people will agree, it's much nicer. So macros allow us to define these special forms to extend the language ourselves. They're written in Lisp, so in pure Lisp, and the results behave, as far as the program is concerned, just like a special form. The nice part of this statement is that they're written in Lisp, and by written in Lisp we mean that everything, all of the functions, all of the libraries, everything that was available to us at compile time is available to us when we're writing these macros, and that's really very, very powerful. So, for example, if you think back to the Python.org blurb at the start, and all of those things that were describing how nice it is to develop in Python, where the nice thing about Lisp is that that's not just true at the point when it's interpreted, but that's true when I'm evaluating logic at compile time in order to turn that into logic that's going to be evaluated at runtime. Yeah. Which is kind of cool. So a trivial example. Here I'm defining a macro. I got this def macro, 7, takes no arguments, and it does 4 plus 3, right? So this looks a lot like the function definition earlier. Can somebody guess what happens here? Any ideas?
Yeah,
so
it returns the literal 4 plus 3. It doesn't do the calculation before returning.
So what happens here, I'm not sure I understood what you said, but I'm going to just, hopefully what I say will coincide. It's similar to a function definition, except that the functions run at compile time. So when I compile, this is run. When it runs, this is now an atom. It is the atom 7, right? So if this was a really expensive operation, that could potentially be quite a saving, because all I do now is say, hey, there's nothing to evaluate at compile time. It's already done.
Completely backwards.
Okay, when should we compile and when should we use it as interpreter?
So there is the concept of compile time. I say compile time because there's an assumption. I say compile time based on the assumption that you're going through first reading, then compiling, then... Now, in the interpreter, essentially what's happening is compilation and runtime at the same time. Yeah? If you think of it like that. So, broadly speaking, in Lisp, you've got read time, you've got some sort of macro evaluation time, but you've got read time, compile time, and runtime, right? And you've got two options. Either compile can be done as a pre-process, or compile can be done at runtime.
Okay.
Right? Depending on how you run things, how you choose. So you can say, you can, let's say think of the Python runtime. So let's say that I'm in a REPL in the Python runtime and I'm running functions. I can say, oh, I'm bored of this function, it's too slow, compile it. And it's compiled. I could do that to all of my source code if I wanted to. I could compile parts of it. And if I don't, it behaves as if it was going compile run. Yeah. So this macro would still get evaluated, but it would get, yeah?
Yeah.
Does that make sense? It would get evaluated when this was red.
Yeah.
Cool. So that's quite nice. So here's something ever so slightly different, and all I've done is add a little quote in front of the 4+3, right? So any guesses now what this does?
This does what I said it was going to do.
This does what Ed said it was going to do, yes. So this returns not the value 7, but the expression 4+3, right? And as I said, I haven't written any complicated code here, but you can imagine that this could be some arbitrarily complex code generation, right, that uses any part of the Lisp library written in Lisp, and all it needs to do is return a data structure that represents some Lisp code, and that is going to, at compile time, get substituted into the function, replacing the call, right? So this is going to, when I evaluate, this is going to be equivalent to evaluating +4,3. But, you know, this is a trivial and slightly useless example, but let's say that generating 4 was a really expensive operation, then it would be quite useful. So that's generally the idea behind macros. I evaluate some Lisp code at compile time, it returns a data structure that represents a Lisp program, and that gets run. And this is why we're now starting to see why the idea in Lisp, at least, of programs being the same as data is actually one of the core ideas and why it's really powerful. So as a little aside, in Lisp we can't really talk about macros without talking about this back quote operator. I didn't explicitly go through the list of reserved characters as they were in Lisp, but this was one of the, whatever they were, 6 or 7, however number they were. So we've got this, instead of the quote, we've got this special type quote, a back quote. And the back quote is essentially very similar to a quote in that it turns this expression into data. But as you can imagine in the previous, let's look back at this, let's look at the problem. Here, this is really nice, but this isn't a very good syntax for defining something that I've constructed dynamically, right? Because this is all hard-coded. I can't really return anything else. None of this is getting evaluated, it's just returning the list of logic, right? If I want to manipulate the list of logic, yes, okay, I can write that and then I can pass it into some functions that manipulate it, but that's not very powerful either. So we have this shorthand. You can think of this as F strings for lists if you've done Python, if you've worked with Python. Yeah, so the idea here is I say it's quoted, but I have this comma that says, the next atom, I want you to evaluate it and put the result in and then return it, right? So in this way we can build some really quite powerful templates that we then populate, with data, yeah, that we substitute for symbols. So hopefully I'll have an example. No. So here we got unless. So this is a macro expansion. Does that roughly make sense? I can't remember if I have any good. That's an example, right? So this is a three-way if macro. And as you can see here, I've got this back quote. Here is some code, essentially like a macro that's going to get replaced. And here this comma A is actually going to be whatever, it's going to be substituted for the expression that gets passed in. So it's going to be do if 0. Yeah. So now we've got a bit more dynamism in that we can build macros. We can build code that takes arguments. Yeah. We can parameterize this We can parameterize this so that maybe macro 7 returns different stuff depending on different things, and we can do it in a way that's actually quite powerful just by the substitution of the code. Yeah, so that's just a little aside. This is eLisp, but most Lisps will have some function, some way of expanding the macros. So I've got this unless it's a macro, it takes A and T, and actually you can see if I call expand on it and pass in the data as quoted, it returns what it expanded to. So this is what I write in the code, and this is what actually the compiler sees, or the interpreter, depending on where you are. And the same for when. I'm going to skip over that. So here, what we've defined is a variation on if. And we've been able to do this thing where we've defined some language construct that isn't only a function application, but also has some control over the order in which things are evaluated, right? And this statement, now I'm not going to go through the actual definition, but this statement contains 3 lists. The first one will get evaluated if it's 0, if the result of the first is 0, the second will get evaluated if the result of the first form is 1, and the third one will get evaluated in the other cases. Yeah, and this is quite a nice way that we can easily extend the language using different constructs. For example, like things like Lisp comprehensions. People have implemented things like that in Lisp, and then they become, because they're compiled and they're part of the language, there's no performance hit from doing some abstraction of a Lisp comprehension that wasn't supported by your language maintainer. So this is one of the really, really nice things. And this is probably one of the nicest things about Lisp, is that if you want things in your language, you just write them. And then they compile and they're part of the language, and that's it. You can extend the syntax. Objects happened in Lisp for this reason. Somebody wanted some objects, they wrote an object system in Lisp to extend Lisp, and then eventually the sort of common Lisp object system that we'll see later, it became part of the Lisp in the base Lisp. But yeah, this is really nice. Note here, because we're talking about note here that I got used else there as a function name. Well, I mean, the point is that I can use words here that are defined as functions, and there are no reserved words, so I can use them, and because I have these because I have macros and two because I think of these symbols as separate from the objects they refer to, I can sometimes play some tricks. And right, so that's essentially all I'm going to talk about the language per se. Does that make a little bit of sense? Is that useful? That sort of. I know it's a bit high level. It's a bit of a whirlwind tour, but actually fundamentally the language is really, really simple. There's not that much to it. Obviously, when you start looking at expressions, some of them are really difficult to read. You know, this is probably about as simple a macro as I could find. But principally because we're not used to the way that we read them. I've left out some things. I've left out, for example, reader macros, which are macros that execute not at compile time but at read time. So if I wanted to implement, so they're just another way in which I could extend the syntax of the language. If I wanted to, for example, implement this backtick, or I wanted to have, and I wanted to implement some character that has special meaning, yeah, I could do that. And I could do that, but I wouldn't probably do that at compile time. I'd do that probably at read time. I'd just modify what was being read, and essentially you have control over the stream and you rewrite it as it gets to the compiler. That's used a lot less, and the main reason that's used a lot less, unless you're either writing your interpreter or you're extending the language with the goal of building a new language. I've seen that used a lot less, principally because it's quite dangerous. So it's global. The change is global. So backtick will mean something else everywhere, even in code that you haven't written. So that's. I think that's a case where
there are no safety protocols.
That is a case where it's way too far, and most people don't use reader macros for that reason. I'm not sure if there are. if there are Lisps where they are, where that's different, I don't know. And generally, I think, from my point of view already, I have way too much power already, so I just don't go there. But broadly, this is most of what we can do. So macros, it's a language construct that allows us to break the rules, so they evaluate things in different orders. It allows us to change the evaluation time, so it can be compile time, for example, or we can mix and match compile time and runtime. That's it. Other cool stuff. So the other cool stuff was partially because on the maybe off chance that Jonas might be here, because I know that he likes some of the craziest stuff. So some of the craziest stuff. Common Lisp has this idea of restarts rather than throwing exceptions, which is really quite cool. I've personally never seen it anywhere else that I know of, but I'm sure there are cases where this mechanism exists. So the idea is that I have a restart form, a form that's restarted, and if there are any exceptions, then I have this try again part of the form that is called to resume, essentially. So this is quite nice with handling, because you can imagine you're processing a list of things, right? And then that throws an exception. And what would normally happen is the exception would bubble up, someone would handle the exception, and then what do? They probably have to have thought about this before and rewrite the program in such a way that they're able to rewind. But this is just a way of saying, well, I've handled that exception, now just carry on as you will. Yeah? And the nice thing is here, and so this is Lisp. One thing that Lisp is actually very good at, and Lisp and probably Erlang and things like that, are writing code that Lisp is one of the few languages that really cares about the image and data within it not dying, right? So you can change the code, you can recompile, you can do all of this stuff with your live data within the process without the process restarting. Yeah. So, and I think this is probably one of the reasons that Emacs is become successful, is that you could change its behavior so dramatically just from within the interpreter, just by rebuilding parts of it, recompiling them, and I'm still using the same data. So this sort of allows that mechanism to be taken a step further, whereas something's happened, I can delegate to some code further up the call stack. That code could try and figure out what went wrong, and then restart. Or maybe if it's really critical that I never shut down, it might say, oh, I can't figure out what's wrong. There we go, programmer, you figure out what's wrong. It'll give you a REPL. You can work out on the REPL, work what's wrong, and then go, okay, cool, sorted, carry on. Right, so these are quite powerful ideas. Restarts, exceptions. Generic setters, quite a nice idea. So the idea here is, you've seen sort of set A1, right? Well, what if I have some complicated expression that I know will return me a result, and I want to set the place that result came from to 1, right? And this is a mechanism where I can do that. So I can say, I can have some arbitrary logic here that happens to return a result, and I want to say, well, where have you got that result from? Now, there's the assumption there that you got it from a variable, but whichever variable you accessed, set that variable to 1. Set the value there to 1. And that's really cool. I think that's really cool. That's something I've not really seen anywhere else.
So it's like your reversing function? It's
sort of, yeah. So it's useful in the cases where it's easy for me to write the logic to fetch something, but maybe it's not easy for me to not so easy to set the logic to know what to set. So yeah, or maybe I already have some logic that grabs stuff, so I can now use the logic to put stuff there. So it's not a particularly difficult concept, right? But it's something that we don't see very often. Reader macros I mentioned. What if I could put code as it's been read? I've also mentioned why they're bad.
But reading macros is basically what happens in C. Or-
Yeah.
More or less.
It's sort of the subset of
Yeah. But in C you can undefine macros. Then you can define some, and then after a while, if you don't want to use it anymore, you can actually undef them.
yeah.
So
yeah.
that's
When
maybe the.
reading macros reading macros I haven't played with too much, so I don't know too much. I think they tend to be operating on the most common is to operate character by character, so that you get a character, but you can move forward in the stream. And basically the idea is that you can read forward in the stream, and you can read it in, you can evaluate it, you can change it, you can write it on. But generally, the first 2 steps of reading, or some of the early steps of reading, of evaluating a Lisp code, are going from the string that you have on file to the representation of the array. Yeah, and you can put something in between those two, right? But most of the useful manipulations we're going to do are going to be with this array, because we've already got a language to be able to manage that.
The array, you mean?
Oh, with the list, yeah.
The list. Okay.
Yeah, we've got a powerful language to be able to manipulate lists. Yeah, it's much nicer than manipulating strings. Now, in other more, let's call them primitive macro systems, it makes sense to manipulate the strings because that's all you've got. But here, it's quite rare that you want to go and manipulate the strings unless you want to do something that really is out of the scope of the ability to manipulate. So, for example, those backticks. Yeah. So it's the only use cases I've really seen is maybe if you want to add single character syntactic sugar. That's sort of that's kind of the only cases. DSLs. DSLs are really quite nice actually. So this isn't really a feature of the language as such, but it's something that comes out of the fact that we can define functions and the programs are data. So I can define this is data, right? It's an array of symbols and some strings. I could have actually not had the print there, could have just maybe been a string. But this is just data. But the nice thing is that I can set up the code in such a way that I can just evaluate that data and it turns into the thing that I want. I think that's it's not really a feature of the language, but it's something really cool that comes out of the design. So the other thing I could say is maybe I want to have this string, and I can change the behavior of maybe the HTML, what the HTML symbol means, and then I can easily have some sort of styling and things that are completely decoupled from my data, which actually happens to be my program. So it's a quite nice example of how the ideas of what the lines between what is your data and what is your program become quite blurred. And clause, I think, is the last thing I'm going to mention. Clause is the common Lisp object system. I haven't actually worked with the object system. Lots of people rave about it. Lots of people say that it's like no object system that's ever existed, but I've never actually used it, so I can't comment. But yeah, fundamentally, you've got the basics there of what you normally have. And you've got some ideas like some sort of multiple dispatch type ideas where I can run functions based on types and all that sort of stuff, so I can sort of get all that kind of goodness. And I think and the last cool thing that we've discussed at length is compile time computing. We've mentioned this with macros. We've got the whole language available. We've got all of your code, all of your libraries, all of your extensions. We can use profilers for the compile time code. The same profilers that we used at runtime, we can use them at compile time. The same debuggers that we used at runtime, we can use them at compile time. And the same errors that get thrown by the libraries at runtime, we get them at compile time. So you don't get any cryptic, the compiler didn't know what's going on, to errors. You get the same set of nice, hopefully friendly, if you've written the code properly, errors that you normally get at runtime. So that's really cool. Thanks, some references. That's it, and so that's it. Cool.
Cool, thank you.